Welcome to the Computational Fabrication Seminar,
a web series showcasing new research, exciting ideas, and exchanging thoughts.
Our weekly 1-hour live sessions rotate through 3 different time zones and are jointly organized at IST Austria, University of Washington, and Singapore University of Technology and Design.
Each session starts with a motivational opening talk given by an expert from industry or a field related to computational fabrication, such as robotics, computer graphics, mechanical engineering, material science, HCI, applied math, design, or architecture.
The motivational talk is followed by a technical deep dive. We invite our audience to ask questions during the talks via YouTube comments and join us afterwards on Discord.
Hi, everyone. Welcome to the Computational Fabrication Seminar. Today, we have 2 speakers, Piotr and Michal, to share their research on perception and fabrication. If you have any question, please post it in the YouTube live chat box on the right of the screen. We will have a short Q&A section at the end of the talks. Our motivational talk is given by Professor Piotr Didyk. Piotr is a senior assistant professor at the University of Lugano in Switzerland, where he is heading a group of perception, display, and fabrication. He obtained his PhD from Saarland University and Max Planck Institute. His research interests include human perception, new display technologies, image and video processing, 3D printing, and computational fabrication. So Piotr, the floor is yours.
Okay, welcome everyone, and thank you for this nice introduction. Thank you for inviting me to give this presentation during the seminar. So today the topic of the seminar is the role of the perception in digital fabrication. And in this first part of the seminar, I would like to introduce the topic, motivate why you would like to consider perception issues, perception into digital fabrication, and then Michal will dive deeper into specific techniques that actually do this. So during this seminar, we have already seen amazing work and techniques for fabricating those amazing structures and materials with prescribed and desired mechanical properties. And this is when the computational fabrication really shines in creating those new intricate geometries and properties of different objects. When you look at the applications of all those techniques that we consider here, there is a wide range of them. So we have rapid prototyping, where we can use rapid fabrication tools. There's new medical applications where you can use those techniques to fabricate, for example, body parts replacements and so on. And there is this other area of all sorts of functional objects, which we essentially, people try to fabricate different objects instead of running a full kind of traditional fabrication pipeline to reduce the cost or to customize objects. And what is really exciting about those techniques and about this development in the digital fabrication is that it allows us to easily customize designs, produce those objects on demand pretty much with the new devices. And also it offers the huge degree of flexibility and complexity with which you can fabricate those objects. But you know, what really I think for me is also very exciting, and what drives the development of this fabrication, is that in general we get a fine control over mechanical and functional properties of the objects that we produce. Now, I would like to kind of look at this fabrication from a different perspective. And what I would like to argue today a bit is that there is also a wide range of applications of fabrication, digital and computational fabrication, where we actually producing objects which are meant for interaction with human senses. And so what I mean here is that oftentimes we not only want the objects to have a proper mechanical properties or have a particular shape. Of course, this is very important, and we can, you know, a lot of developments are in this direction. But oftentimes, even for prototyping, from medical applications, or for example, heritage preservance, we also want to produce objects that look in a certain way, or they feel in a certain way. And in those applications, what is important is the reproduction or production of desired appearance properties and desired haptic properties. So just to give you an example, a toy example is, what if we wanted to fabricate something that feels and looks like this kind of leather case? Well, fortunately, we have today those very capable devices, 3D printers, will offer us a wide range of different 3D printing materials. So one possibility is to simply choose the material that closely matches the material that we desire, with the mechanical properties and maybe appearance properties that matches what we want to produce, and essentially try to print or fabricate from this material the shape which is as close as possible in terms of geometry. However, very quickly we will realize that even with the abundance of different printing materials, this will not give us best results. So here, what is also interesting is that those new devices, especially 3D printers, besides this wide range of materials that they offer, they also deposit those materials and mix them at very high resolution. So essentially, our prints are built of tiny voxels, where each voxel can be kind of printed with different materials. And this, what it allows us to do is to essentially, if we have a given object, the given geometry to fabricate, we can use those, what we call primary materials, or those materials that we have available on the printer, and essentially create the mixtures of those materials to simulate or to get so-called meta materials, which essentially can kind of provide the mechanical properties in between all those materials that we have available on the printer. And this is a very interesting solution, because essentially it allows us to widen the range of material properties that we can achieve using those techniques. And now the problem becomes in computing the material mixtures that matches our desired properties in the best way. So essentially, in this kind of formulation, the problem of fabrication or computational fabrication is we have some input geometry and we have some properties. We will later talk about haptic and appearance properties, but in general, we can say we have some kind of properties which we want this object to have. And the goal is to essentially compute the material mixture which reproduces those properties. So one thing that you can immediately realize is that the space of possible solutions is huge, because those devices, the multi-material 3D printers, can deposit the materials at very high resolution. So it means that we have billions of voxels that we deal with, and each of these voxels can have a different material. So there is a lot of possibility in essentially arranging those materials to get the desired properties. Now, those techniques are one way of formulating the solution to such techniques is to formulate an optimization where we essentially optimize for the material assignment to those different voxels such that they describe the properties. And to do this, we essentially have mainly like two steps, where for the given material assignment, we should be able to simulate the properties that the current material assignment gives us. And then we should be able to evaluate with sort of error metric or error measure how close we are to the desired properties. And essentially, this error measurement guides the optimization towards our goal. And this is not very yet specific to the perception and what we would like to talk today about. But it's important to mention also that this kind of pipeline was used to fabricate or to design techniques which for fabricating appearance and mechanical properties without actually really considering in depth the perception. However, today what we would like to focus is how actually we can facilitate this process using some insights from perception. So I was saying there are like two crucial components. There is simulation and error measure that we need to have in order to run such optimization. So let me start with the error measurements. So if we consider the fabricating objects, which should essentially have a certain haptic or appearance properties, the question that arises is, how do we quantify even the haptics or appearance properties of the object? What do we measure? Fundamentally, those properties are multidimensional properties. So this is another problem that we have to address. And the other question that you may ask is how accurate we have to be, how accurately we have to reproduce those properties. So just to give you an idea what I'm talking about here and why this error metric or error measurement is important is when we, for example, again, consider the haptic properties, and the human sensory system kind of builds the sensation of the haptic properties using different properties of the surface. So we sense essentially the roughness, the compliance of the surface, maybe the stickiness, the warmth, and so on. And now using all those properties, we kind of build the overall kind of perception of the surface. So this is what I was saying, that this is essentially a multidimensional problem, because the error measure, which should guide our optimization to produce objects with desired haptic properties, should maybe account for all those properties. But the question is how to quantify them and how to weight them, which are more important, and so on. And the other aspect and the importance of this error measure is essentially comes from the fact that even though current 3D printers can produce a wide range of different objects, and you know, this is really amazing, very often we end up we have our goal is kind of outside of what the current 3D printer can print. So in this case, this optimization that I was talking about, you can think about this as a mapping from the space of all possible objects that we may want to design to the specific kind of region in this, what we call the printer gamut, and mapping of those designs to the kind of subspace which represent the objects which can be actually fabricated. So, okay, so what's the role of the error measure? Well, the error measure here will essentially guide this mapping, and will essentially, depending on the error measure that we are using, we may get different solution and different material mixtures, which will be used during the fabrication process to represent our designs which lie outside of what 3D printer can print. So, you know, speaking about this error metric, again, that the simplest solution, if you think about it, if I want to fabricate this leather case, is, well, I can simply go ahead and optimize the mechanical properties of the material and maybe microgeometry. And what is interesting, I will not dive here into details, but you will see in the following part of this talk, which will be given by Michal, that such a solution is suboptimal. And if you consider perception, you can actually get much better results. And the other aspect of this optimization kind of pipeline is the simulation. This simulation, because the problem, as I said, the dimensionality of the problem that we are trying to solve is huge, the efficiency of the simulation is a key. But also efficiency, but also the accuracy. Again, if you look at the touch perception and the haptic perception, we as humans, we are able to detect very tiny differences in the structure of the surface, and we use different mechanoreceptors to pretty much resolve some differences up to 1 micron. So the simulations that actually guide those optimization, on one hand, have to be able to kind of simulate those those effects on very fine scale. But on the other hand, as you will see in the Michal's talk, you can actually leverage some limitations of the sensory system to speed up those computations. So, okay, so how do we realize this kind of, how we put this perception into this pipeline? To do this, essentially, what I refer to the perception aware fabrication is some kind of solutions which lie and research and techniques which essentially on one hand are inspired by the perception, so the core perception field which analyzes different properties of the human sensory system, and the computational fabrication. And the goal essentially of those techniques and this kind of work is to still investigate the human perception and run experiments, but build the computational models which can model our perception. And then on the other hand, we want to use a computation. We want to use the hardware limitations, accounts for hardware limitations and constraints, and build so-called perceptual optimizations, which kind of take inspiration from both of those fields. And the core of those techniques and of those computational models, one way maybe of doing this is to creating so-called perceptual spaces. And what the perceptual space is essentially embedding of different stimuli in the multidimensional space. And what is interesting about this multidimensional space is that the Euclidean distance in those spaces, it corresponds to the perceived dissimilarity. And those perceptual spaces, they are not really new, like in terms of the haptic and appearance, those things were considered people, as you can see here. We're building those perceptual spaces by analyzing different stimuli. The problem, however, is that to derive those spaces, you need extensive perceptual experiments where people compare different samples. So this already poses some problems in terms of generalization of those models, which we would like to have. But the bigger problem is the fact that when you derive those spaces are derived for the stimuli that you use in experiments. However, in our optimization, we would like to be able to put into the space and compare to all other solutions or our other stimuli new designs. And the problem is that those dimensions of perceptual spaces, they're usually not well defined. And putting on the fly the new design or the new object to this perceptual space to compare it to other objects is not really possible. So what you will see in the Michal's talk is the solutions which actually try to make sure that those dimensional perceptual spaces, the perceptual spaces that we derive, they're actually correlated with physical attributes. And this is the important property and important feature of those techniques that have to be maintained. And once we have those perceptual spaces, the idea essentially follows the optimization pipeline. So you have a parametric design, we have a numerical simulation, which now output those physical properties, physical attributes, which build the perceptual space. And we essentially formulate the perceptual loss. Now, just to summarize the challenges here when realizing such optimization, the numerical simulation have to leverage the limitation of the human sensory system, has to be efficient. It should account for devices' limitations and predict actually the required physical attributes such that when we run the simulation, we can actually compute this perceptual loss, which guides the optimization. And this perceptual loss should be essentially efficient error metric, which accounts for perceptually relevant properties and handles this problem of dimensionality, meaning that we have many different cues for example, resolving the haptic properties or the appearance properties. And here the idea is essentially to use those perceptual spaces because those physical attributes that are provided by the simulation, they directly could relate to the dimension of perceptual space. So as we have a current design, if everything is designed well, we can directly put this object into the perceptual space and measure the distance and therefore the similarity in the perceptual space sense to all other solutions that we considered. So with this, I would like to give the stage to Michal to essentially show you how those challenges and this general optimization pipeline can be realized for such problems as compliance and optimization of the haptic feedback of drawing tools. Thank you.
Thank you, Piotr, for the motivational talk. Our deep dive talk will be given by Michael. So Michael is a postdoc at IST Austria in the computer graphics and digital fabrication group, led by Bernd Bickel. He obtained his PhD at the University of Lugano under the supervision of Piotr. His work lies in the cross-section of fabrication, perception, and numerical simulation. The main objective is to leverage the limitations of the human sensorial system to design more efficient and more intuitive fabrication methods. So, Michael, the stage is yours.
Thank you very much for the kind introduction. Let me share my screen. So, thanks again for the introduction, and also thanks to Piotr for his great motivational talk. And in the second half of the seminar, we will look into the other portion where Piotr explained why we would like to investigate combination of perception and fabrication. We now look into how we can combine perception with computational fabrication. And in this talk, I will describe how to build upon computational models for perception, then demonstrate how they work on practical examples, and motivate some possibilities for future research. To start, to show you how to derive a perceptual space, we will start with a case study on compliance perception. We will see how to investigate human perception, build a perceptual space, and extend it with a computational model that can be used to enhance computational fabrication of objects with prescribed deformation behavior. So we interact with elastic objects every day, and we check fruits if they're ripe, or our muscles if they have grown. Or at the moment of the pandemic, we might be checking our bellies if they have grown instead. The importance of creating objects with desired deformation properties sparked research that enhanced the possibilities of printing elastic materials. But what is an elastic object? When a physicist looked at an elastic object, he can describe it as the amount of force required to compress it a certain distance, or the so-called force displacement curve. But when we, as humans, investigate compliant materials, we do not perceive numbers. Instead, we perceive feelings such as stiff or soft. And these feelings depend on many cues. Besides the already mentioned force displacement curve, there is texture, where rougher objects are generally associated with also being stiffer. Visual cues, where the peak on the middle looks softer than those on the side. Heat transfer, where cold materials are associated with stiffer metals, and others. And to build the perceptual space of compliance, we have to first investigate how we perceive elastic objects. So to this end, we prepared a set of 3D printed stimuli with varying stiffness, and then we invited participants to a psychophysical study. During the study, the participants were presented with 3 samples, a reference, and 2 possible reproductions, A and B. And their task was to poke them with their finger and tell us which of the reproductions is closer to the reference. And our task is now to analyze this data and design a perceptual space. So we recall that a perceptual space is a multidimensional embedding in which the Euclidean distance corresponds to perceived dissimilarity. However, this distance is a priori unknown, so we need to recover it from our psychophysical experiment. When we take a closer look at the study, we present the participants with a reference, design, and 2 possible reproductions. And we ask them to mark which reproduction is closer to the reference. And therefore, each trial in the study gives us a constraint on the distance between a set of stimuli. And this distance further depends on the location of each sample in this perceptual space. So this leads to a constrained optimization of sample locations in an n-dimensional space that satisfies all the collected constraints. And we performed this analysis for our samples and found that the perceptual space of compliance is one-dimensional. Further, we scale the space in JND, or just noticeable difference units. When 2 objects are 1 JND apart, it means they are easy to distinguish. And on the other hand, when they are below 1 JND, that means they are hard to discriminate between them. So formulating the JND has a direct application for computational fabrication, as it serves as an objective stopping criteria that we can use for quantifying a sufficiently good reproduction. Unfortunately, the recovered perceptual space is challenging to use in practice. As Piotr mentions, since it was recovered in a perceptual study, we do not know how to embed new samples into the space without running additional experiments with including this study. And since during optimization, we constantly produce new designs, this is highly impractical. So what we do instead is to design a computational model for perception of compliance. And we do this by identifying the governing physical phenomena of the computational model. And our key insight in this project is that to formulate the computational model, we use both physical quantities and interaction with the sample. And is motivated by the fact that the force displacement data is measured by a machine which can apply much more force than a person could, or would in many situations. So as a result, our judgment of compliance will be affected by our interaction mode. So to characterize the interaction, we use our previous experiment. During the user study, people continuously poke the blocks, and depending on the strength of each poke, they explore a different part of the force displacement curve. We have recorded the applied forces in time, and now is a question of how to store this data. We can note that the interesting part of the interaction happens at the peaks, that is when a poke ends. So to characterize the interaction, we store the force peaks in a peak force histogram. We use the peak force histogram to formulate our analytical model. The intuition behind our model is that if we were dealing with linear materials, the slope of the force displacement curve would govern the stiffness. However, with nonlinear materials, the slope can be defined only locally. So we calculate an expected value of the slope by doing an average of the local slope weighted by the force displacement data. And the proposed analytical model has an excellent match to the empirical perceptual space. So to recapitulate, I will show you that the perceptual space for compliance is one-dimensional, and to place new materials into the space, we can use an analytical approximation based on the force displacement measured and expected interaction with a sample. Unfortunately, what happens when we want to estimate the compliance of this 3D model? We would need to physically manufacture, measure the object, and give it to participants to estimate the expected interaction. In fact, this process has to be repeated for every iteration of the optimization. So instead, we propose to use a numerical approximation of the model. For the numerical approximation, we need the force displacement data and the expected interaction. We replace the measurement with a numerical simulation where a finger-like indenter interacts with the object, and we recover the interaction from a database of interactions that we stored during our psychophysical experiment. So to recapitulate, to apply perception-aware methodology for manufacturing objects with prescribed compliance, we replace the numerical simulation with our computational model that uses both a physical simulator and a data-driven estimation of expected interaction. And then we compare samples based on their predicted interaction and the force displacement data. So now we can look at some example applications. Imagine we would like to fabricate the object that you can see on the screen, and we don't know how stiff it should be. So we would like to explore the available space of stiffness. The 3D printers can print using many combinations of material, and it's costly to manufacture all options. So instead, we propose to uniformly sample materials from which to pick. And to generate this sampling, we place all the models in the perceptual space and pick equidistant samples. And here we can see that our selection on the top is compared to the current state of the art on the bottom, which was there at the moment. And we can immediately see that the state of the art method fails to select perceptually distinct materials and suggests two that are nearly identical. And this motivates that we could improve the current optimization algorithms. As mentioned before, the algorithm takes a geometry and force displacement data and outputs an optimized object. And at the heart of this process is the optimization driven by an, at the moment, still L2 norm. However, since L2 norm does not shine at detecting a perceptual difference, it is possible that a perceived undistinguishable curve is found much sooner than the converged one. So instead of letting a standard algorithm to converge each iteration, we measure the current perceptual error, and if it's small enough, we stop the optimization. And during the experiments, we have found an interesting example. When optimizing for the following curve, we got the converged and perceptually cutoff curves. So far nothing out of the ordinary. Since L2 curve is optimizing the area between the two curves, it is obviously closer on this diagram. However, we also look at the perceived difference. The cutoff curves has an unperceivable error below half a GND, and on the other hand, the converged curve has an error above 1 GND, which means it is a much worse reproduction. To explain this behavior, we investigated what is our model focusing on. Since our model works on slopes, we plotted the slope-force relationship. First the target curve, then the converged and cutoff curves. As you can see, on a portion of this graph, the perceptually cutoff curve is much closer. And this becomes even more accentuated when we plot the peak force histogram and find out that this is where most of the interaction with the sample will be happening. So, in conclusion, This was a great case study for perception-aware fabrication. On one hand, we saw the benefits of the approach in designing more intuitive tools and producing higher quality reproductions than state-of-the-art results. On the other hand, we also revealed some challenges of this approach. First, by running a triplet study, the cost of the psychophysical experiments grows combinatorially. Second, even a relatively simple one-dimensional space required significant experimental effort to identify the governing physical attributes. And third, to map new designs into the space, we relied on numerical model with off-the-shelf simulation that was expensive to evaluate. So if we want to apply the methodology to more complex problems, we need to tackle these three challenges. And we will see how to deal with these challenges in the second practical example, when we will design the haptic feedback of drawing styli. With recent releases, the digital drawing tools started to gain traction as they promised to integrate our workflows with the conveniences from digital world like undo and layers that boost our productivity and creativity. Unfortunately, the advantages of digital drawing come at a cost. A digital stylus and a tablet lack haptic feedback associated with traditional tools, and this haptic feedback is important for creating precise strokes and crucial with missing hand-eye coordination. And these factors motivated solution to the problem that attempt to reintroduce the haptic feedback via varying the stylus tip, the tablet surface, or attempting to digitize drawing done by traditional tools. On the other hand, researchers experimented with providing the haptic feedback through active modulation with vibrational motors. This appealing idea is, however, hitting limits of the current hardware. The latency of the motors used to actuate the styli degrade the perceived realism. Instead of feeling a surface under stylus, we feel the stylus itself vibrating. Therefore, to achieve a realistic reproduction, we want to design a passive stylus. However, how good are the current commercial solutions? To answer this question, we use a perceptual space of drawing tools, which is one which I will describe how we derived that later in the talk. In a custom optimization, we correlate the axis of the space with physical measurements, and this enables us to place digital styli into the space. And we can see that commercial solutions are only a small subset of haptic feedback produced by drawing tools. And to understand why, we first need to investigate what happens with a tool during drawing. The haptic feedback of a drawing tool is governed by the coupled frictional contact of the drawing instrument with the underlying substrate. And when we zoom in, we can see that the paper substrate is not smooth. It is formed by compressed cellulose fibers. And during drawing, fibers of different size impact the drawing tool. And this impact causes resistance to the motion, which wears down the instrument, and the worn material is deposited onto the drawing substrate as the visible stroke. As we can see, the physical behavior is complex and consists of many phenomena. In order to identify those relevant for haptic feedback of drawing tools, we conduct a psychophysical experiment. So as stimuli during the study, we used pencils with different hardness, fine liner, ballpoint pen, and charcoal. We also considered multiple drawing substrates, a rough paper, standard office paper, and stone paper. And similarly as before, we opted for a forced choice experiment. A participant is first presented with a reference drawing tool, then two possible reproductions, and the task is to choose which of them is more similar to the reference tool. However, here we immediately must tackle the first challenge of perception-aware fabrication. Since having only 15 stimuli leads to over 1,300 triplets, making our user study infeasible to conclude in practice. So to get an intuition how to address this challenge, let us investigate what happens during our experiment. During our user study, we are recovering the percentual chance of preferring sample A over sample B. And this, in general, correlates with perceived distance via a sigmoid function. To make the study feasible, we should take a closer look at the correlation function. People have noticed that the more we prefer one sample over the other, the less precise our estimates are. This is due to the exponential rise in the function that requires exponentially more trials to precisely evaluate. And on the other hand, when samples are similar, we need significantly fewer trials. We can also argue that such cases are more interesting as they are hard to decide. So what we can do to make our user study more efficient is to focus more on the samples that are very similar rather than on those that are distinct from each other. So we can show you the evaluation strategy on an example. Let's say we have 7 triplets, and at the outset of the study, we do not know which of them are similar. So what we do, we evaluate each of them a constant number of times in an exploration step, for example, 2 times. After the exploration step, we identify the cases which are hard, for example, those that resulted in a tie. And then we isolate these cases and exploit this knowledge and evaluate them multiple times to get a precise assessment of their distance. Finally, to optimize for the perceptual space, we use all the samples that we have recovered. And this to not artificially bias the space and remove from it the knowledge that certain samples are very distinct from each other. To optimize the perceptual space, we use a probabilistic formulation. And the formulation is searching for an embedding which is maximizing the likelihood of observing the perceptual study that happened in real life in real life. So after the optimization, we recover a perceptual space that matches the user study as well as possible. However, here we hit the second challenge of perceptual fabrication, and that is identifying the governing axis of this space such that we can put a new tool inside without having to run additional user studies. And traditionally, and also in our first project, this would be done by inspecting the space and guesstimating a transformation that makes the space correlate well with desired attributes. And often complex transformations which perturbs the space are necessary. And this leads to a trade-off between correlation and expansion of the experiment that is in general manually tuned. So to eliminate the manual tuning, we enhance the optimization with an additional term. This term guarantees that the axis of the recovered space correlate well with the desired physical attributes. And by jointly optimizing for both factors, we can guarantee good correlation and optimal fit to the data. So finally, I will present to you the perceptual space of drawing tools. First, we add tools on rough paper, then tools on office paper, and finally tools on the smoothest stone paper. To avoid the quality of the space without the ground truth, we use bootstrapping. This technique checks how sensitive our space is to varying the input by random subsampling. We can visualize this as a cloud of points around each tool that represent our certainty of the position in the space. We can observe that the space follows our intuition. Pencils and charcoals form visible clusters in the space. We can also observe that while we are certain of placements of the pens, we are less certain in placement of the pencils. This is likely caused by the wear of the tools, which can alter the haptic feedback during the perceptual studies. So the recovered perceptual space can be directly used as a loss function during optimization. And since we correlated with perceived friction and vibration, we also know what are the physical attributes that we need to numerically model such that we can evaluate this for arbitrary generated designs. To design a numerical simulator for optimization, we need a couple of criteria. We need to be precise and efficient. If we have a precise simulator, we should model rigid tools that require stiff systems. Additionally, we should include frictional contact with wear and material deposition. And both of these requirements are in contrast with having an efficient and fast solution. So what can we do to make the task easier? We start with an exponential error integrator. To recover the new position of a stylus, we need to solve an integral that is composed of two terms. Geometric term representing the stylus shape and material, and forcing term representing external forces acting on the stylus. And the forcing term is highly nonlinear and can quickly make the simulation impractically slow. So the challenge to keep the integrator efficient is careful handling of the forcing term. And the first thing we can note that all the external forces that are acting on the stylus are just one-dimensional time-varying signals. Therefore, we can use Fourier decomposition and represent them as a sum of sinusoids. This is very important for two reasons. First, it allows us to formulate an analytical solution to the problem. And second, we can exploit limitations of human perception to accelerate our simulation. In general, our perception of vibration follows a U-shape that peaks around 250 Hz. In the regions below 50 and above 500 Hz, we are regarded as insensitive to vibrations. So here we can make a very important observation. We can simulate only the sinusoids in the sensitive region and save the computation time on effects, which would not be perceivable and appreciable by the end user anyway. And now we know how to efficiently model the behavior of rigid tools that require stiff system. There is one more thing that we need to do. We need the force signal that drives the stylus. And this force is very complicated to recover as it depends on the drawing paper, the tool, as well as our hand grip and pressure. So instead, we exploit another property of our simulation, and that is the integral at the beginning, which allows us to pre-simulate individual results and combine them with correct weighted combinations on the fly. This makes the simulator ideally suited for a data-driven forcing term. To train our data-driven term, we considered three drawing surfaces ranging from rough to smooth, And we also considered 3 different materials and 3 different tip sizes. This results in 27 individual measurements that we use to train our data-driven forcing terms. We model the surface as a set of sinusoidal forces with different amplitude and frequency, and this represents the stylus hitting asperities of varying size at varying time intervals. Next, we modulate the forcing term with 2 scaling factors. The first scaling factor models the material of the stylus, and the second models the tip shape. The combination of these elements results in a full-scale simulation. And please note that the motion was enhanced to make it visible, and our styli were not vibrating this much during the studies. So to validate our simulation approach, we took 2 styli that were already in our database and created an interpolated styli with interpolated tip and material properties. We measured its behavior when drawing on paper and also predicted the behavior with our simulator at various speeds. And we can see that we achieved a very good match. The last missing piece required to completely recover our tool descriptor is the friction. And to this end, in our data, we found that Coulomb friction model fits our measurements well. So this allows us to model the friction as a single coefficient, and to obtain the friction of new tools, we simply interpolate tools that are already in our database from the data-driven fitting term. So to summarize, to apply the perception-aware methodology to design of digital styli, we start with a parametric design, we evaluate its physical properties with our custom numerical simulator, and finally compare it with desired target in the perceptual space. And that leads to an update on the parametric design. We have applied this method to a design stylus that better matches a pencil when writing on a glass tablet. When we look around in the perceptual space, we can see there is no good match for a pencil, and a better tool could be designed. We use our simulator, and in a line search algorithm, we generate interpolated design, simulate its behavior, place it into the perceptual space, and repeat until we achieve the best match. To validate our claim, we conduct a user study where we presented the participants with all the tools you can see on the slide and asked them which is the best match for the pencil. And 83% of people preferred our design. We can also revisit our original goal of designing better styli than commercially available. We first add into the perceptual space the commercial styli, and then our 3D printed styli on artificial surfaces like glass and screen protectors. We can see that our new tools have significantly better coverage than commercial alternatives. Unfortunately, they still cover only a very small portion of traditional tools. And interestingly, when we add our tools on real surfaces like papers, we can see that the coverage improves drastically. And this tells us that to faithfully reproduce the haptics of drawing tools, we need to model both the stylus and the geometry. And in fact, this is what we focused on our second project, and the second practical example in designing haptic tools, where we designed both the surface and the drawing stylus. So in this project, we push the passive stylus design to its limit by searching for a mapping that maps a traditional tool along with its substrate and a manufacturing process into a printable design that feels the same. And in this talk, I will show you how such a mapping can be performed. Not only that, but I will also demonstrate that it is possible to mimic the feel of traditional tools while using drastically different materials, plastics versus metals and graphite, and an order of magnitude coarser geometry that does not resemble the paper substrate at all. However, the joint interaction of the design stylus surface combinations results in a haptic response similar to that of traditional tools. So to design this mapping, we can take various approaches. A direct solution to mimic such interaction would be to attempt to manufacture the substrate and drawing tool geometry. Unfortunately, such a straightforward solution is not feasible. On one hand, each manufacturing process operates with a limited selection of materials and precision. Moreover, when modeling contact at such a fine resolution, the fabrication imprecisions have a significant effect on the resulting haptic response. On the other hand, while we want to mimic the haptics of drawing tools, there are physical phenomena that are impractical for digital styli, like wear and material deposition, that would be better to not reproduce. So an alternative solution would be to use the simulator from our previous work. And just a quick reminder, to estimate the haptic of the stylus, we used a custom numerical simulator where a data-driven term represents the surface of the tablet, and an analytical integrator solved for the behavior of the stylus. And while this method can capture a wide range of haptic feedback, it is not suitable for surface design. This is because we optimized only for the stylus shape, and the surface was approximated with a data-driven model, which would then not be able to predict novel surfaces that it has not observed. So the key to mimic a wider range of haptic feedback is to jointly optimize for the stylus and the driving substrate such that their coupled interaction reproduces the desired haptics. Unfortunately, when optimizing for the coupled behavior, it is not feasible to use numerical modeling. As in many complex design tasks, the state-of-the-art methods do not currently offer predictive modeling at rates and scales that can account for the numerous coupled physical behaviors governing the haptic of styli and surfaces, nor for the limitations and uncertainties inherent in their fabrication process. So to address these challenges, we propose to include fabrication into the optimization loop. However, utilizing fabrication during optimization is not straightforward. When we manufacture and measure a digital design, it is unclear how we can utilize this information to generate a new stylus. Since the printed stylus acts as a black box and does not provide us with derivative information, the high cost of the objective function makes the derivative-free optimization infeasible. And lastly, a simple gradient descent is likely to get stuck in a suboptimal local minima due to the high non-convexity of the objective function, which comes from the interaction coupling. We propose to tackle these issues with a Serograde model. A Serograde model is a data-driven proxy that models the fabrication process, and we will use this proxy to optimize for new designs. So, to design the Serograde model, we have to take into account that we are dealing with a physical manufacturing process, and that process has errors and imprecisions. And these imprecisions manifest as noise in the observed data that we need to model. Therefore, we assume uncertainty in our predictions. And in particular, we assume that the uncertainty can be explained by a multivariate Gaussian distribution. Under such assumption, our Serograde model is known as a Gaussian process. In our work, we use two separate processes, one for predicting the perceived friction and one for perceived vibration. To predict the location of the tool, we feed the parameters of the digital design into the Gaussian process and get an estimated location in the perceptual space. The workflow is then that we generate a new design, place it into the perceptual space, manufacture it, and update the Serograde model to generate a new design. So the question now is, how do we use the information we gathered from this event to suggest a new design that brings us closer to the desired haptic feedback? The vanilla formulation of Gaussian processes is used for function minimization. And in contrast, in our case, we seek a specific value of perceived friction and perceived vibration. So to this end, we formulate an acquisition function, which task is to suggest new designs based on perceived data that balance the exploration-exploitation trade-off. At the start, we have a target behavior and a digital design that is currently the closest match. We can measure their distance, which then defines a circle of improvement. To pick the best designs from within this circle, we can maximize the improvement function. Unfortunately, since we are dealing with Gaussian distribution, we do not deal with simple numbers. Instead, we have to calculate the expected value of the improvement. And to see an illustrative example, imagine we have a design for which we know the vibration and we would like to estimate the expected improvement in friction. The friction of the design is defined as a Gaussian distribution over all possible frictional values. And to calculate the expected improvement, we collect all frictional values within the circle of improvement and multiply them by the probability of happening. However, this leads to a nasty numerical solution since the maximum operator inhibits solving the problem analytically. So therefore, we propose to model the maximum implicitly. Therefore, we propose to model the maximum implicitly by setting tight integration bounds. And this allows us to reformulate the maximum as a two-sided integral, which is integrating within a square region. And such a formulation has an efficient analytical solution. So in summary, to create digital designs that match the haptic feedback of traditional tools, we propose to start with a parametric design, generate it, physically manufacture it, measure it, and place it into the perceptual space of drawing tools. Based on this interaction, we update the Serograde model that predicts the perceived friction and vibration. Finally, we use our acquisition function to generate new designs. So now you can see our optimization in action. Since our formation is data-driven, we warm started with a set of styli and surfaces. In the perceptual space, we can see that none of the initial samples is a close match to a ballpoint pen on a rough paper. So we therefore run our optimization that proposes a new design that we fabricate, manufacture, measure, and place into the perceptual space. The optimization first focuses on designing new surfaces. However, this quickly gets it stuck into a local minima of what it's possible to do with the styli that were in our initial set. So it proposes a new stylus design, which allows us to escape this local minima and run into a new family of surfaces, which eventually leads into a reproduction that is almost indistinguishable from the original tool. So finally, here we can see the original tool and our optimized tool side by side. And we can make some critical observations here. While these two tools manifest the same haptic feedback, they are composed of entirely different materials and geometries. The stylus uses rubber-like plastics in contrast to the metallic ball in the ballpoint pen. And the digital substrate has features orders of magnitude coarser than the paper. And in fact, it does not resemble the paper substrate at all. And we optimize for multiple traditional instruments, and you can see that the trend of drastically different materials and geometries continues. Let's take a moment to enjoy how cool this is. We can reproduce the haptic feel of a drawing tool while manufacturing something that does not resemble it at all. This proves that it's possible to make materials like pencils and papers that are too fine to directly manufacture and reproduce them on a 3D printer, thereby increasing the apparent gamut of the manufacturing device. And to evaluate our drawing tools, we invited casual participants and professional artists. The casual participants were asked in a blindfolded scenario, and the casual artists in an open-ended survey. The overall consensus is that our tools provide distinct haptic feedback, feel better than the commercial alternatives, and are hard to distinguish from the traditional counterparts. The artists shown even interest to demo our tools during their work in the hopes of doing digital only during production and ditching traditional drawing instruments. So we can also revisit our original goal of reproducing haptic feedback of traditional drawing tools. We can see that by picking the correct manufacturing process, we can reach any point within the haptic response of traditional drawing tools. So in conclusion, today we learn about the perception-aware fabrication methodology. From psychophysical experiments, we construct computational perceptual spaces that can be applied to increase the apparent gamut of a 3D printer. We validated the methodology in a case study of compliance and showed its benefit to design of objects with prescribed deformation behavior. We further improved the methodology by proposing optimized experiment designs, more robust likelihood-based optimization, and a perceptually coarsened numerical model. We presented the application of these improvements to the context of digital drawing tools with prescribed haptic feedback. Lastly, we have shown that it's possible to increase the apparent gamut of a 3D printer. We propose that the key component to achieve such a goal is optimizing the reproduction in the perceptual space, which allows us to cherry-pick the desired physical properties like roughness and friction, while avoiding unwanted phenomena, for example, wear and material deposition. However, the techniques presented here today have applications beyond the projects that you saw. The perception methodology was already adopted to investigate the tactile perception of roughness by teams and colleagues, and this work was presented at SIGGRAPH. Similarly, we have seen interest in applying our likelihood-based optimization to more general datasets. The idea of perception-aware coarsening can be applied to optimize numerical simulation in varying challenging domains, ranging from tactile properties to sound reproduction. And lastly, our fabrication in the loop optimization goes against the established approach to replace slow manufacturing with faster numerical simulation. And by embracing the limitations of the fabrication process, we can efficiently create data-driven models that encode not only the governing physics, but also imperfections of fabrication process down to differences between individual machines and material batches. However, the story does not end here. So far, we have only scratched the surface of haptic reproduction with a stylus. The more general problem of mimicking the haptic feel of materials investigated by our fingers is still an open and challenging one. However, the results we have demonstrated for drawing tools suggest that it is not necessary to slavishly reproduce the microstructure of a surface to capture its haptic feel, and that the degrees of freedom we will get by utilizing a proxy surface can be leveraged to enable general haptic optimization. Another area of possible future work lies in appearance reproduction. A considerable body of work investigates how our eyes perceive various stimuli and materials on digital screens. However, it is unclear how these studies generalize to reproduction of appearance in the physical world. Interconnecting these two areas has the potential to give us deeper insights into how the physical materials have to be deposited to best match the desired look of a material given a limited set of primaries available on the 3D printer. And the last section can be a bit far-fetched, but we are already seeing some first devices capable of creating experiences for our taste buds and our noses. And having a computational model of what constitutes good food can be advantageous not only for fabrication, but also to guide the designs of new recipes and similar. So with that, I would like to thank you for having the opportunity to present on this seminar.
Thank you, Michael, for the inspiring talk. So currently there is no questions from the audience. So maybe I ask a few questions first. So the first one is for Piotr. So nowadays in graphics community, we know there are lots of work that use machine learning to solve various problems. For example, shape synthesis, all these kind of things. So are you considering to use this learning method to solve perception OL design problems?
Yeah, this is a good question. I think there is also, like, as you mentioned, there is like machine learning techniques present in the graphics community, but there are also already some works that try to, you know, use machine learning to kind of compute the low dimensional embeddings of the stimuli. So for example, you know, what Michal was doing is kind of more directly deriving the dimensions and physical attributes that describe those perceptual spaces. But it's also possible to use machine learning to essentially learn those spaces and possibly create the simulation techniques, which essentially use machine learning techniques to bring you to the perceptual space. So in a sense, like, yeah, it's possible to train machine learning methods to essentially to represent or to learn essentially those spaces.
One thing, so we know for this perception is quite subjective. So for example, if some expert he is very strong in percepts some visual stuff, is that possible to learn from his skill or knowledge? Well, for example, we can record some data from his perception, and then we use this to help us to design something. That means to train. The meaning is that to employ to utilize the knowledge of the experts to help us to design, but based on a learning method.
I'm not sure.
Okay.
Are you asking whether we can use the, because like we didn't, like, you know, we are not experts in drawing, right? So I think you refer to experts who essentially use those for example devices daily. So one aspect of that is definitely, I'm not sure whether this was really your question, but maybe I can mention this, is that when we design those spaces and we create those optimization techniques, and they are kind of done based on the experiments which are run on kind of, we call it an average user, right? So they represent some population, and then therefore they are not specifically targeting certain groups of users. It's possible, and you know, we observe also this during our experiments with drawing tools, that some people would be, you know, because of what they are doing, even for a job or for a hobby, they are sometimes more sensitive than other people, right? So those methods, because we design those spaces using essentially for an average user, like they would not represent this kind of oversensitivity or like increased sensitivity to certain things. And this we also observe both in haptics, but also in vision, like in the work that we've been doing also in my lab about the human visual perception. Like we noticed that people essentially who are experts in certain things, they're more sensitive. Like if you think about images and artifacts in images, and if you ask people who do the rendering, like they would be super sensitive to things that other normal people would essentially not notice, right? So it's kind of like a kind of learn sensitivity to certain things. And this is definitely, you know, in terms of haptics as well. And, you know, when we were doing those experiments, we also kind of saw that we are becoming more sensitive because like we kind of know those things and what to look for and so on, right? So in one aspect, this can be kind of overcome in a sense. And, you know, in some works show that you can essentially take those computational models or perceptual spaces and kind of customize them, in a sense, personalize them. So it would be possible to kind of, the question is how you personalize them, because you don't want to run the whole experiments for one person, because those are large experiments, but that would be possibility to essentially kind of customize those models and target specific group of users. I'm not sure whether this answers completely your question.
Yes.
Okay.
Yeah, that makes sense. Okay, I have one more question for Michael. So, okay, your talk is very interesting. So you design something that to reproduce a drawing tool with given haptic feedback. So one thing I'm not clear to me is what is the application of these techniques? So because I already have some drawing tool can draw the things, why I need to produce an alternative?
Mm-hmm. So the haptic feedback is essentially very often requested by the artists. And when you ask them, it sort of starts with something a little bit more abstract to the point of, I like it. Mm-hmm. However, there is an implicit reason why they actually like this. So there is a significant body of research that people are learning and interacting with the tools very often based on their haptic feedback. And this is then sort of engraving into you how the tool can be controlled, and it allows you to control the tool with much more finer details. So while you can relearn yourself to draw on a tablet without looking at it, or you can relearn yourself to have more precision while you are looking at it, it will be always for you more natural to just draw with the tablet without directly interacting with it. And this then sort of constitutes this abstract feeling of I like it more, where they don't really have a concrete reason why they actually like it more, but implicitly they like it more because it's more controllable, more intuitive for them to use them.
Yeah, that's true.
Yeah, I wanted to say that there's also a bit of a background story behind it. And I think Michal will agree with me that we've been working on this haptic reproduction, and, you know, we were thinking at the beginning of producing surface that would mimic certain feel with a direct touch. And we even started experimenting with this. The task is relatively difficult, and the difficulty comes from essentially this, what I was mentioning also during my introduction, that there is like a dimensionality of the problem. Like we, as a human sensory system, we have many different cues, which allow us to essentially recognize certain surfaces and build like the perception of the surface. And we essentially kind of, when we started working on this, we realized that, you know, you cannot address like all those cues right away. And you have to kind of limit yourself a bit. And essentially in interaction with a probe, because that's what it really is, right? Like when you draw on the surface, you essentially interact with a surface with a probe. It essentially gets rid of some cues, and it makes a bit the problem easier, because you essentially, you know, you reduce the dimensionality. You don't have to account, for example, for the heat transfer, for example, right? And so the problem becomes a bit easier, and that's, you know, and then we thought that, you know, that this is something that we can address. And we, you know, and there was this application of drawing tools, which we found some quite interesting. And we're also collaborating with, you know, with, for example, Danny Kaufman from Adobe, who was also interested in, you know, essentially reproducing the digital, the feedback of drawing tools in case of digital tools.
Yeah, that means there are lots of things to explore. So now we just start at some I mean, a small step.
Yeah.
Okay. So there is no question from the audience. So probably we move to the Discord for a non-recorded discussion. Okay. Thank you for the nice talks.
Thank you very much.
Okay. See you in Discord. Okay. Bye.